All right, we'll go ahead and get started. Welcome to the FDT Group and OPC UA Technology webinar on empowering a approach to enterprise integration, hosted jointly by the FDT Group and OPC Foundation. Thank you for joining us today. My name is Maggie Carlson with the FDT Group, and I will be your moderator for today's event. Before we begin our presentations, I want to make sure everyone is familiar with the attendee control panel on the right side of your screen. There are 3 features that will help with interactions during the event. First is the question box, where you can type your questions during the presentation. Those questions will be collected and read aloud at the end of the event for answers by our technical experts. Please note that because this is a webinar, we will only be able to accept questions by the question box and not live by phone. If we do not get to every question, we will be sure to answer those questions by email. Second is the handout box. We have made overview and technical brochures available to you for download on FDT and OPC UA. Please feel free to download and review. Third is the chat box. If at any time you run into a technical issue, please feel free to use the chat box and send a message to the organizer or staff. Let's get started. This webinar highlights the latest collaborative developments and the role the FDT for OPC UA Information Model Companion Specification plays in evolving digital architecture transformation for the new era of automation. Supporting brownfield and greenfield applications, the unified solution empowers the next-generation industrial workforce with open, flexible deployment options, allowing sensor-to-cloud, enterprise-wide connectivity. Now let me introduce you to our technical experts online with us today who will be presenting. Glenn Schultz, Managing Director of the FDT Group, Stefan Hopp, Vice President of the OPC Foundation, and Thomas Hadlick, Architecture and Specification Chairman for the FDT Group. Here's a quick look at the agenda set for today's webinar. We will kick off with an introduction from the FDT Group on the technology, including a look at the new FDT IIoT server architecture known as FITS. Then we will move on to an introduction from the OPC Foundation on OPC UA technology and its communication and modeling framework. From there, an in-depth presentation on the FDT and OPC UA collaboration efforts will be given, along with the results of Project 1, including a demonstration of FDT integrating OPC UA and Industry 4.0. We will get a peek at ongoing initiatives for the collaboration with Project 2, and we will end the event with a Q&A session. All right, Glenn, let's move on to the introduction of FDT.
Okay, thank you, Maggie. I'll give you a brief introduction to the FDT organization. So the FDT Group is a nonprofit organization. We're headquartered in Belgium in Europe. We're a membership-led organization, so we have all the leading automation firms, instrument and device vendors, a number of notable universities, and some of our very large users as members of the FDT Group. As an organization, we're focused on the design, promotion, support, and advancement of our FDT standards, and we do that through at any one time, 200 or so volunteers from our member companies working for the FDT Group. We've had a technical collaboration with the OPC Foundation since 2011, sponsored by Tom Burke and myself, and you'll see some of the results of that throughout the presentations today. From a standards perspective, the FDT standard has a history of more than 15 years. It's the most widely deployed industrial automation standard out there in the industry for engineering, commissioning, configuration, and maintenance. There's tens of millions, if not more, of FDT-supported devices and systems installed in the field. And probably what's recognized as the strength of the FDT standard is that it supports all major industrial communications protocols. And we can tunnel through any stack of these networks to get to the end device, and this all happens transparently to the end user. We are recognized worldwide by all the major standards organizations. Our most recent acknowledgement came from the China government. We are now a national standard in China. If you haven't worked with FDT before, just to help you with some of the thoughts that are going to be presented today, here's a few quick terminology things that'll guide you throughout the presentation. In the FDT standard, our primary method of getting access to device is called a device type manager. This is a device driver that's provided by the device manufacturer, and it represents the device in an FDT system. Inside that DTM is the business logic and a very advanced graphical user interface that supports all the functions of the device, such as configuration, diagnostics, prognostics, and documentation. The other term that you'll hear throughout today is the FDT frame, and this is simply a host system that's compatible with the FDT standard that can leverage any number of DTMs in a project structure to gain access to the networks and associated devices. The standard interfaces for the FDT standard expose rich device and network information. So from a device perspective, we have online and offline context. There's identity, status of the device, health of the device, parameters, ranges, documentation, and so on. But we also have information related to the projects and the network. So we have the topology of the network, the health and status of the network itself, and the configuration of the network available in the FDT standard. Today, our current release of the FDT standard is version 2.0. You'll see this commercially in the marketplace. It's reflected as FDT 2. We're about to release a minor update to FDT 2.0 as 2.1. It's been approved by our membership, and some minor new features and editorial enhancements will be part of this release by the end of the year. Then we have our new standard that's coming up that builds on top of FDT 2.1. It'll be publicly available by the end of the year. It's our FDT Internet of Things Server, or FITS. We're currently prototyping it with membership. Its primary features that it enables browser and app connectivity. It enhances the OPC UA functionality, which will be the subject of today, and it's deployable in a cloud through desktop topology. Here's a brief introduction to FITS. If you look at our current standard, the FDT 2 and soon 2.1 standard, you'll see that the DTM has two parts. On the bottom is the business logic, and on the upper part is the user interface. These two components in the DTM communicate through the frame application. The standard also supports a client-server architecture. In this version, it implies a thick client. So the client you see at the top of the diagram is a Microsoft-based client. It contains part of the frame and then the DTM user interface. That's serviced by a common server on the bottom, which has the other part of the frame application and the business logic of the DTM. We take that basic architecture, so here we have the frame and the business logic from the DTM, and we build on top of that for our FITS initiative. This protects a great deal of the investment that the vendor community has made into the FDT technology. The business logic remains the same. All of the FDT well-defined interfaces are the same, and we continue to use our developers toolkit called Common Components to enable this platform. The clients will be operating system agnostic from the beginning, so any web browser will be able to access it, and any app built on top of any development system will also be able to access the FITS server. We anticipate that a future release will also allow the server to be deployed on any operating system, although the initial release will be a Microsoft-centric operating system. From an architecture perspective, this is designed to be highly scalable, so it can be deployed in the cloud to support an entire enterprise, or it can scale all the way down to a standalone desktop type solution. Then we take that core server and we wrap some things around it. On the upper right, you see web services. We have a control portion, and of course the topic today for OPC UA. The web services supports browsers, apps, and any standalone application that cares to access the FDT information. The OPC UA connectivity enhances that even further by allowing enterprise information exchange, and we'll get into great detail on this section today. And the control side is, in one way, our traditional control network connectivity, so we retain all the network support and tunneling and so on that we have today, but it also adds capabilities to do this in the cloud with secure connections to remote facilities. Here's a quick look at using the web services part of FITS. So you can see it's direct support for browser apps, even augmented reality as we've demonstrated in some of our recent trade show events. Connectivity can be through any means that clients can connect. And because we are talking about remote access here, we do have a very robust layered security model that's based on industry standards. Here's a look at a sample app that could be built on top of the FITS server. Here you've got an app for a maintenance person. They enter an asset tag number as they're working out in the facility, and then they can select a number of options such as launch the DTM to do a full-blown interaction with the device, or maybe they just want to see the current process value or assess the health of the device, or maybe they just need the manual. So apps like this will further extend the FDT solution because now the workflows can be tailored towards the work and the individuals so they can work smarter, and in a case like this, they can get equipment working again faster. From a security perspective, this is a quick look at the security model. We start on the outer layer. The security has TLS underlying it, so it's completely encrypted communications using well-established industry standards of HTTPS and WebSocket Secure. The next layer down, we're able to authenticate devices themselves in the architecture, so not only the users that are on that device, but the device has to be authorized as well. Then we have user authorization, and finally inside of that, the underlying technologies of HTML5, JavaScript, and so on. To connect to the various control networks, there's a number of ways that this is possible, but in any case, tunneling and nesting holds true in all scenarios, so we certainly can still directly connect to a traditional control network, but we can also achieve secure remote connections through VPN, MQTT, and other methods. This supports any type of cloud connection, edge devices, VPNs, Azure, and so on. And it also allows a single server to take care of multiple plants and locations. So anything enterprise-wide in a cloud example, as you see here, or it could be a simple desktop application as well. From an OPC perspective, we support, of course, the secure OPC UA connectivity that's well established. And what's done with this is almost unlimited, as many of you know from the OPC side of things. So you could connect to PLCs, MESs, ERPs, clouds, enterprises, and so on. We'll support the publish and subscribe, and of course we can exchange any data that's available in the FITS server with OPC UA clients, and Dr. Hodlick will get into this in great detail shortly. So just from an overview perspective, this is what perhaps a fully deployed FITS application could look like. You've got the server sitting up in the cloud, and you have secure connections to all remote points, whether they be browsers, apps, smartphones, and so on. Similarly, the connections to remote facilities are well secured, and of course, any OPC UA clients that are connecting to the FITS server remotely are also well secured. And with that, Maggie, I turn it back to you.
Thank you, Glenn. All right, thank you for a nice presentation. Now let's go ahead and switch it over to Stefan with the OPC Foundation on an update on OPC UA. Take it away, Stefan.
Thank you very much. This is Stefan Hoppe, Global Vice President of the OPC Foundation. I give you a short overview on the foundation. The foundation has clearly the vision to provide industrial interoperability, scaling from sensor to IT enterprise and cloud in a completely secure, reliable way, but also, and that's critically important, in a complete independent way from vendors, independent from any kind of operating system, platform, or languages, but also independent from any kind of domain. Sure, we grow up in the industrial space, but also we are growing now out into other areas. The OPC Foundation itself is an international non-profit organization where both IT and OT companies meet. So we have traditional automation companies, for example, on the board of director, like Siemens and Yokogawa and others, but also we have IT companies like Microsoft and SAP on the board. And what we deliver is an international standard also. And as you see here on the map, we are globally in every most critical important regions of the world, and we will continue growing. For example, this year we started Korea and other areas. I'm pretty proud being located here in Europe, which is providing 50% of the members of the foundation. What is exactly what the foundation is delivering? First of all, the specification is an international IEC standard, which is public available for everybody. You just have to register on the OPC web and can download it. You don't have to be a member. Second, code. We deliver stacks in different languages, which is also available on GitHub as open source. But here we have a so-called dual license. Also, non-members can download the code for evaluation. That's fantastic and great. But if you want to use it, you have to either join the OPC Foundation, or you have to open the code on your side also, or you can also, of course, buy a toolkit. And I highly recommend to make use of a toolkit. You get a jumpstart, you get consulting, you get fantastic proven quality. This is the best jumpstart you can do. The OPC Foundation is also providing developer tools for testing and so on, and of course certification. And this is what we have, certification labs in different areas and continents of the world. And also these labs, we changed the business model. They are open now also for non-members for a high amount of money, so certification as a service. We provide face-to-face meetings in each continent once per year, but you can also test your products virtual. Overall, OPC Foundation is to collaborate with other organizations like we do here with the FDT group, and you find the logo of the FDT group in the first line in the right area. Overall, the idea is all these organizations model their data, define their interfaces, but then make use of OPC UA for the secured access and transport via different protocols. As you see, we are in different markets. It's from automation, oil and gas, energy. It is for live data, but also for engineering data and the engineering process. You find also, by the way, the landing page for the FDT group here on this link if you want to get more detailed information. So let's look what is OPC architecture internally. Critical important, and that's why we marked it red. It's an architecture, not a protocol. OPC UA is not just another protocol which you should or can compare with other protocols. It's an architecture, and the lower level blue line is really that we have our own data model, data description with all data types, and with built-in information models like live data, historical data, alarm and conditions, and so on. On top of that, other organizations, we are talking about the green box now, are exactly now implementing their information model. And this is exactly what the FDT group also has done. But you see also other groups like the PLC Open or BACnet for building automation and so on. So on top of that, of course, if vendors support and follow this standard, of course, vendors have the possibility to implement their own services if they want to differentiate or if they want to use additional services only internally in their company. From a access point of view, if now a machine or a device vendor or a software vendor is implementing OPC UA, the information model, OPC UA provides a client-server architecture, a one-to-one relationship, which allows to connect to a server, to browse its namespace, to read the capabilities, to read-write nodes, call methods, and do subscriptions to receive callbacks. All these services are completely independent from the lower protocol level, which means exactly OPC UA, the transport level, is extendable and future-proof for the future. And this is exactly what's happening right now with the so-called PubSub implementation. While on the left side, the client-server architecture is really a confirmed communication based on TCP, a one-to-one relationship. The PubSub is an unconfirmed communication, which is super fast in a broadcast way. For example, we are supporting UDP, which you might use inside a factory to share data from one data source to a lot of listeners, but also AMQP is directly implemented to be one of the cloud protocols to allow directly seamless integration from OPC data points into cloud systems. We are extending this also with MQTT following soon. Here's the overview and the information and the architecture. And again, you see that the protocol part of OPC UA is only the red box. And that's why OPC UA is much more than just a protocol. It provides industrial interoperability with different information models, live data, alarm and condition, historical and machine and program states. And other organizations are using this to transport their information in a completely object-oriented way, completely scalable. I give you two informations about where OPC UA is adapted in the world and also in other consortia. The Industrial Ethernet Consortia have published their connectivity framework, and OPC UA overall is today included into 3 test beds all around the globe in different scenarios. In the initiative in China called Made in China 2025, OPC UA is already part of the specs are already national standard, and part 5 and plus the rest will be continued to become a national standard in 2017. For Industry 4.0, I like to share this information. OPC UA has been already recommended as the only communication layer in the RAMI Reference Architecture Model Industry 4.0, which has been published in July 2015. And inside this RAMI model, there are 2 layers for communication and information where OPC UA clearly makes sense. Because of the relevance to the German Industry Initiative 4.0, the German Federal Office for Security has analyzed the OPC UA spec, but also the reference implementation, and has given a very positive public report, which you can find on the OPC Foundation, but also the BSI web. It's called OPC UA Security Analysis. So we are really proud that our software solution, our platform has been proven by experts. On the right side, you see that the Z4E has already made a criteria catalog, how to fulfill, what are the criteria you need to fulfill to name your product Industry 4.0 Basic or Ready or Full. While the levels Ready and Full are not really completely specified today, it's for the future, you already can check if your product is fulfilling the basic requirements. There are 7 criteria, and 2 of them are listing OPC UA. One of them is listing OPC support mandatory. So download that from the Z4E web. And because of the relevance, the VDMA, which is the European largest association of machine builders with more than 3,200 members, published an Industry 4.0 communication guide based on OPC UA, which is not explaining OPC UA itself, but explaining how you can integrate that, what are the steps and the migration steps into your factory. If you want to have more information and deeper information, we have pretty good brochures which are available in 5 languages, which is not just marketing and testimonials. It's also a very deep dive into the technology itself, plus security, and a couple of information models from other organizations. And we also have videos with a deep introduction for the technical introduction, but also on the security and multiple others on the companion specifications. And of course, you can contact me in case there are any questions. With this, I hand over again. Thank you.
All right. Thank you, Stefan, for your presentation. Just as a reminder, if you have any questions during the webinar presentations today, don't forget to go ahead and enter those into the question box area on the right side of your screen. And Thomas, let's go ahead and get moving with the collaboration efforts and discuss the results of Project 1.
Okay, so thank you. And I would like to present to you the FDT OPC project. This project has started in 2014 with a kickoff meeting in March, and then the target was definition for an implementation of OPC UA servers based on FDT2. FDT2 then at this point of time was very new, and basically what we wanted to do was define an OPC UA information model to represent the information from the DTMs, and we wanted to define a mapping from information provided by the DTMs into the OPC UA information model. And why did we start this project? So OPC is considered as a very important interface, especially for integration into higher levels of the functional hierarchy. So I'm talking about manufacturing execution systems, MES or ERP, and also device manufacturing. Also, we considered OPC UA as an interface for integration of mobile applications for device diagnostic and configuration. We have demonstrated this and already in some shows there are OPC UA clients that can be executed on mobile platforms. And last but not least, OPC is important, as Stefan explained, for use in Industry 4.0, and I'm going to have some slides on that also. So within Project 1, basically we executed following steps. We selected a number of use cases and described those. We considered which information access is necessary for supporting these use cases, looked at what is the description of information on both sides, OPC and FDT, and then basically provided the FDT group specification. And last but not least, we implemented an OPC UA server and prototype that served as a proof of concept. This is a slide coming from FDT2 specification. So when we designed FDT2, we already considered using DTMs in such an environment. So starting from the right side, you see basically here a network of devices, a small hierarchy consisting of several field buses. And in the middle, you see the frame application hosting DTMs, and each DTM represents a device. So we have a DTM representing the field bus interface, and also DTMs representing field devices or the gateway. And for the mapping to OPC UA, we need an OPC UA information model, where again these devices are represented. So we have a node representing the field bus interface, and then also nodes representing the different field devices and the gateway. And the OPC UA client can access this information model via the OPC UA interface. And basically, if he accesses that interface, the information is retrieved from the DTM and provided back to the OPC client. Stefan showed this, already explained this already in his slides. So basically, we took advantage of that architecture and used an already existing companion standard as a base OPC UA for devices. And on top of that, we defined our own information model for FDT to represent the FDT information from the devices. How does it look like? If you look at an OPC UA information model, it consists at least of 3 parts. You have the type section, where data types and different object types are defined. You have the object section, where the actual object instances are invoked, and also where basically the real data lives. And you have the view section, where you can define views for selecting the information for specific applications. Okay, so what we did was we defined FDT-specific data types. We defined an FDT device type as a base for device types represented in DTMs. And then we defined a way how a device would be represented in the object space. And for representing of network topology, we are using the OPC UA for devices definition. So basically, when looking at the use cases that we support or we provide information about the network topology, information for identifying the device. We want to be able to get a list of available device parameters. Retrieving device status should be supported. Device diagnostics, reading parameters offline as well as online data. Of course, also writing back and auditory was supported. So these are basically very simple use cases, but we think they can be used as a base for supporting more complex use cases. For instance, when you talk about condition monitoring, they are based on being able to access online data or being able to access device diagnostics, and then basically the data needs evaluation, and this evaluation can be provided by the OPC client. We started to look how does the DTM provide information. So this is also a figure coming from the FDT2 specification. When we looked at this, the first thing that we noted was, okay, it doesn't show that the DTM also supports diagnostic data. And then basically we see the DTM provides device type information for offline identification as well as online identification. We have different types of data, device parameters, which are provided with some description like value range, access information, semantic information, and the actual value. I/O data, here we have only description, we cannot provide the value. And then we have network configuration, the graphical user interface of the DTM, documentation of data, so that's the current values of data actually. Something that's also provided by the DTM are documentation, so DTM can provide manuals, different types of technical documentation certificates, as well as device descriptions. So it's actually mandatory for some DTMs to provide things like EDS or GSD. Also, it's possible to support device description based on ProList and eClass or eTIM. And yes, the device status is provided according to NE 107. So all this information is available from the device. Basically, now we had to think about how to map it into the OPC information model. So we started basically with device type information. Device type information mainly is supported by DTM information. It's also type information in the FDT space. And this information then is mapped into the type space in OPC UA information model. Actually, if you look at OPC UA for devices, they also define that the serial number is provided here. And with FDT, we are able to retrieve the serial number only when we access the device online. So we defined the mapping for the serial number for the instance space in an online case. So this is a representation of the communication network as defined by OPC UA for devices. If you have a very simple network consisting of a station and two field devices connected via, it looks like Profinet network, then basically this is represented in the object section of the OPC server. And there's a device set which basically contains all the devices. So a station is represented as a device, and the field devices are represented. And then there's a network set which represents the networks within the topology. So PN network is represented here. And each device provides connection points, and the PN network basically references the connection points in different ways. So we have a connects to pairs or plain connects to in order to represent the network topology. This is very powerful, but also if you look at this information within plain OPC client, within generic OPC client, it's also very confusing and hard to read. So, okay, representation of a single device basically is done based on the type definition. So in the type section we have a specific device type, and the device is inherited or inherits information from that. And then the device provides a parameter set, which is a flat list of all parameters supported by the device, and a device method set, which is a flat list of all the methods related to the device. And then there's something, a construct called functional group type, basically that can be used to provide a more human-friendly way of representation and organization of the data, similar to a menu or a drop-down menu. Using that as a base, we defined a mapping of the information from the DTM to the OPC namespace. So the DTM has an interface called iFunction, or an interface ID base data. iFunction basically provides graphical user-based functions or functions without user interface, and functions without user interface can be mapped to the method in the method set, and the device data can be mapped to variables in the parameter set. What we also do is we use the functional group type in order to provide a more human-friendly representation and access to the information. So having defined that, we implemented a prototype, and this is basically the hardware that we typically use for our demo. So it's basically a current sensor, so a sensor for electrical current by Weidmuller, and Vega pulse, so a level sensor provided by Vega, and then we have some equipment in order to connect that. So that's a hard USB adapter and also a network interface. So look, and I have that equipment here standing next to my desk, and basically we are using that also for the demo now. So this is a very typical FDT frame application. So the frame application has a project section where it can provide or where it provides the network topology. So you see here I have the USB adapter, that's the Vega device, and here we have the communication interface for Modbus TCP and the Weidmuller device. And these are normal DTMs, basically where that you can use in a normal way. So that's the Vega device. And actually, I can show you the connection, online connection with a Weidmuller device. Okay, we see now they are connected, and if I start an online function, the connection becomes active, and then we see the value of the device. So that's for observation purposes. So I'm going to shut down this frame because we use the frame this frame application to define the project which is imported into the OPC server, and take some while. Okay, and then basically with the OPC server, it imports the project structure, starts all DTMs, and reads the information from the DTMs in order to create the information model. If I use an common or generic OPC client to look at the information model, basically here we have the type section. So in somewhere deeply buried in the type section, we have the device types, FDT device type. So basically, these are the different devices that I can represent with based on FDT. So these are the devices that are supported by the DTMs that I have on my laptop here in my environment. And the devices actually within the project are shown in the objects section in the device set. So you see the Vega device. These are the Weidmuller devices, the Modbus interface, and the hard adapter. And when you look at the information provided here, you get the identity information, who's the manufacturer. So surprisingly, it's Vega, or the device model. It's a Vega Plus, Vega Pulse, I'm sorry. And then basically we get a lot of additional information. The parameters are provided in the parameter set in a quite large flat list. There are also some methods related to that. Okay, and so these are the device set, and actually down here we see the network set providing the network information. So this is not very user-friendly. That's why we have created a specific FDT client. The FDT client works with the information provided by the OPC server. Everything you see here is basically transported via the OPC UA interface. So that's the network topology that we just saw in the OPC UA server. The images are also transported via OPC UA. And then when you look at the representation of the devices, it's much more nicer. So we are able to see the identity information for the device. Also, an DTM can provide device documentation. So for an example, I have here the user manual for the Modbus COM DTM. So this is an PDF document. You just saw how a PDF document was transmitted via an OPC UA connection, and this would work also remotely. Then what else can we show? We have the offline data, so the device parameters. These are basically functional groups provided by the DTM. So the DTM can provide the parameters within hierarchy, and we display that hierarchy in the OPC namespace as functional groups. You see, this is a prototype. It's not complete. The constant value hierarchy that the DTM provides is much too complex for us at the moment. Okay, and also we can access online data. So if I go online with that current sensor, okay, the status, for some reason this device says I should check the function of the device, but I still am able to retrieve the values. Takes a little while. Okay, there we go. So that's the currently measured current that the device reports, and something that we did basically. So this is a software from April last year. So prior to the FITS initiative, we were looking at if we are able to transport HTML user interfaces. So that's basically an HTML dialog provided by the server, transported as a string and then displayed here, and we are able to populate the data based on the data coming from the OPC UA interface. So something else that we did is in respect to the Industry 4.0 initiative, and device, as I said, can provide its a device description also based on E-class. So this is provided as an XML file. That's why it doesn't look so nice in the Internet Explorer. So this is basically an E-class description of the device, describing the properties. You see, these are the E-class identifiers and then the respective values. Reading this is not so nice, so that's why we provided with the OPC server an implementation where the descriptions are translated to with a label, and then the label as defined by E-class, and then the values become much more readable. Okay, that basically concludes the demo. Let me jump these slides talking about the demo. So basically, as I said, the DTM supports a lot of information. With the current prototype, we are able to support quite a lot of information, but we are not able to provide description of the I/O values or support network configuration. DTM graphic user interface at this time is not really supported. Documentation of data is not supported. Okay, so based on that, basically we started in May this year a second project, and that's what I'm going to explain in more details in the outlook. But first I would like to explain something related to Industry 4.0. So Stefan already introduced to you the reference architecture model for Industry 4.0. So I just want to point out some specific access to you. So here we have the access for the hierarchy. So that's basically the equipment hierarchy that we have in production systems. So this is based on ISA 95, going from product, field device, control device, station, work center, and so on. And the other important axis to remember is the Z-axis. So it's called layers axis, or it could also be called the aspect axis. It starts from the asset, which is basically what we mainly see here as device, and then somehow we need to do something to integrate the device into Industry 4.0. We need a standardized communication, for instance, OPC UA. We need a standard for representing the information. the functions provided by the equipment, and also the business rules related to the equipment. So basically, the layers section describes what is necessary to do for integration into Industry 4.0. In order to do that, basically each asset, which is shown here as a gray box, needs an administration share. The asset can be composed as shown by the smaller green boxes, but each of the assets basically is represented by an administration share. It provides the virtual representation and technical functions. An administration share and asset together are called Industry 4.0 component. So having that in mind and coming back to the reference architecture model, we are now looking basically on the one side defined by the equipment hierarchy and the z-axis, and basically when we look at this, in the asset layer, we see the specific assets, and all the other layers are provided by the asset administration share. And together they represent the Industry 4.0 component. And something that we know for sure is that for different types of assets, we are going to need different asset administration shares. So when I look at this from point of view of FDT, we are looking at the field device, the Industry 4 component for field device. Okay, that these are some examples for field devices. We think that integration can be done with a DTM, and that all other layers will be supported by an OPC server, OPC UA that provides OPC UA for FDT. So that also includes the information layer. So if you look at the information layer, there are certain expectations in regard to the asset administration share. So the expectation is that the administration share provides identification information related to communication, engineering, configuration, and so on. And this information actually is defined already by several different standards. The expectation is that the information is provided in a format defined by Digital Factory. Okay, so how is this done? When we look at a specific asset, for instance, the temperature transmitter, it is hosted or supported by an administration share. The administration share can access the sensor via field bus communication, and on the other side provides Industry 4.0 conform communication. So here we talk about OPC UA. And via this transportation, the asset provides information, and the representation of information basically occurs in an information model according to Digital Factory. And the important part here is basically the expectation that a value is basically identified with a specific identifier called IRDI. And the IRDI basically explains the meaning of the value. So from the information or from the expectation that are already defined for an asset administration shell, with our prototype, we are able to support identification information, engineering information based on E-class, and configuration information based on FDT. So when you look at this, basically we have the field device. The DTM with additional information is providing the integration. So additional information means here manuals or integration of for a large variety of field bus protocols. Communication access is provided, supported by OPC UA, and there we don't care which transport mechanism is used. The information is organized in form of an OPC UA information model based on OPC UA for devices and on mapping for IEC 61360. The functional level, we provide functional description of the field device. So basically, what function does the device provide, and also supporting functions like diagnosis. We hope later on will be able to support also graphical user interface, and we think that the business rules will be defined by the frame application, by the environment which provides the OPC UA interface basically. Okay, so very short, the technical outlook. Project 2 was started in May. We selected the use cases to support, are working currently on what is necessary to support those use cases, and basically the description and the specification or the prototype is something that we do in a later step. Looking at the use cases, we selected priorities for the different use cases. So one very important part is that we do prototyping for FDT 2.1, which is about to be released in end of this year. Also, we think that support of I/O description and I/O data has a very high priority, and currently we are doing the integration with FIT server. Other less important topics are support of documentation of data, so basically report generation, support of network configuration or direct access to communication channels is something that we consider to have very low priority. And the support of the remote graphical user interface basically depends on the results of the mobility project. Okay, and that's basically the end of my presentation. So
thank you, Thomas, for a great presentation and demonstration on how FDT and OPC UA empower a single approach to enterprise integration. Thank you very, very much. This concludes our presentations for today's webinar. And open it up for questions. If you haven't already submitted any questions into the question box on the right-hand side of your screen, you may go ahead and do so at that time. And we have a question. How is the DTM information mapping done to OPC UA? Is it device by device or per device model / DTM?
So I guess that's a question for me. It's done at the moment with a prototype. It's done device by device. Okay, the device type information is done once for each device type, but the actual values, the actual provided parameters are mapped device by device.
One question that we had earlier at our earlier call was, and this one is for you, Stefan, what is the importance and main applications of OPC UA?
The main importance is that we are explicitly not talking about any protocol or any operating system. Exactly, OPC UA is completely independent on that because it starts thinking on what kind of data and interfaces do we want to share to the outside world, independent if this is a device or a machine or just a software service. And by sharing the data and the description and the meaning of the data and the interfaces, plus adding security and access rights, and being able to transport this over multiple different protocols for multiple different scenarios, this is a real deep benefit of having this combination of OPC UA as just an enabler. OPC is nothing more. It's just an enabler, because the real value is to add exactly the information, what we learned here today with the FDT information model. This is the real value behind everything. It's OPC UA is just the enabler, like you have a USB memory stick where only the connector, the part, the standardized connector, well, is the enabler, but the real value of the USB device is exactly the functionality behind, which might be a storage device or a DVD burner or whatever, right? And that's exactly why it scales from small embedded systems up into IT enterprise systems. So every FDT-enabled device or scenario, for example, is automatically out of the box connectable to applications from SAP or Microsoft Azure Cloud within just 20 minutes with fully security integrated. So overall, we are talking about standardizing engineering efforts and reducing efforts for the topic of engineering. That's it.
All right. Well, thank you, Stefan. Are there any additional questions before we leave for today? Okay. Well, I think we're up against the hour here, so I would just like to thank all of our presenters today. Thank you so much for the informative collaboration and the demo and everything else that was presented. We thank everybody for attending the webinar. We hope you enjoyed it. Today's webinar was recorded, and the link to view it will be sent by email when it's ready. Thank you for attending today, and everybody have a great morning, afternoon, or evening, wherever you may be. Goodbye.